Hello everybody, this is Mr. Strager here with the notes for our first section 1.1. Now, in class, we chose to skip over a couple of the definitions here, these first three, mainly because these are really going to be coming into play during geometry, which is the 10th grade standard math class. We won't be talking about these at really any point in this year. It's just to prepare you for next year. However, we do have a couple of definitions that we would like to work with. The first one is an equation. An equation is just a statement that two expressions are equal. And this doesn't just need to be in mathematics. For instance, you could have something like puppy equals doggy. And I think most people would agree that these two are pretty much equivalent in the eyes of, let's say, a toddler. In general, though, in mathematics, if it has an equal sign, it is an equation. You can even have something like this. 12 equals 7. Now, obviously, 12 does not equal 7 on any world that I'm on. Because it has an equal sign, it's still an equation, just an incorrect equation. But an equation nonetheless. Following that, we're talking about linear equations in one variable. A linear equation in one variable is sort of like a type of equation. It's any equation that can turn into this form. Now it looks like nonsense, especially because we're talking about one variable and here there are three. That's why in class we discussed how, in general, whenever we're talking about a general form of an equation, you're going to replace some of the letters in here with whole numbers, or more specifically, constants. As a reminder, constants are just numbers that are not variables. So the rule here is where A and B are constants. And A doesn't equal 0. A and B have to be constants, otherwise there's just too many variables. Everything in this equation can change, and it's sort of hard to keep track of what happens when it changes. However, the other rule is A cannot equal 0, because if it did, 0 times x is 0, meaning all we'd be left with is a number equals 0. That's not what we want. So that's a linear equation in one variable. An example of this would be something like if we replaced the a with 3, the x stays the same, and if we replace plus b with plus negative 7 equals 0, that's a linear equation in one variable. The solution to a linear equation is a fancy way of saying what's left over once you have just your x on one side. Once your x is all by itself, or your y, or your z, whatever variable you use, that's the indication that you've solved the problem. You are finished. And all that's left to do is to check your answer. We're almost done with the vocabulary, everybody, but next up we have inverse operations. And inverse operations are extremely important when we're talking about any type of equation solving. This is sort of like the key to everything. Here's the idea. Let's say I have the equation x plus 3 equals 5. If you were to read this out in English, it would be what plus 3 equals 5? And you would have to figure out what x is. Now many of us might instantly say 2, and that's great. That's forward-thinking mathematics. That's where you have the answer in your head before you really have any process in mind. It's very good for solving things very quickly, but in this class you also have to be able to show how it happens. The thing is, when it comes to this equation, we want to get x all by itself. Wouldn't it be nice if this plus 3 just disappeared. If it wasn't there, we'd have an answer. In math, we have the opportunity that we're going to talk about later to actually change this equation by adding, subtracting, multiplying, or dividing something to both sides of the equation. Both sides referring to both sides of the equal sign. To do this, we have to use what's called inverse operations. And the inverse operations are just two operations that undo each other. Two operations that undo each other. And the key with this is the word undo. Remember how I said you want to get rid of the plus 3? Well, we have to undo plus 3. How do you undo adding 3? Well, that's where the inverse operations come into play, because the inverse, or opposite, of addition is subtraction. So in this case, we have plus 3. To undo it, we would have to do some kind of subtraction. Specifically, if we wanted to get rid of plus 3, we would have to do minus 3. It's always the inverse of whatever number is after your operation, even if it's a negative number. So to get rid of plus 3, we subtract 3. The other inverse is with multiplication and division. There are more inverses that we're going to talk about later on, but those are going to come much later on in the class. However, while it would be nice if we were just able to subtract 3 and fix all of our problems just by basically randomly doing operations, we can't quite do that. Because if we took a look at the original here, we would see that x plus 3 equals 5. Many of you might have already guessed that x is going to be 2, because 2 plus 3 is 5. If I changed this equation here, well, plus 3 and minus 3 make 0, so we can cross those out. We'd be just left with x equals 5. But x can't equal 5 if x is supposed to be 2. There's something else we have to do, and that's where equivalent equations come into play. Equivalent equations are equations with the same solution. When you have the power to change equations, you have to make sure you change it in a way that your variables stay the same. So if I subtract 3 from this side, x would be 5. We don't want it. We want x to be 2. But remember how I said you can kind of add, subtract, multiply, or divide anything as long as you do it to both sides of the equation? Well, if we subtracted 3 from this side, how can we get 5 to equal 2? Well, we would have to subtract 3 from this side, and that'll give us 2. This is a very core property to mathematics. Whenever you want to do something to one side, you have to do it to the other side of the equation. These are the properties of equality. If you look down at the bottom of the page, you'll see the addition property, for instance. The addition property says, let's say I have something like 3 equals 3. To keep this equation equivalent, to make sure that it has the same solution, let's say I wanted to add something to the left side. Let's say I wanted to add 1, plus 1. The properties of equality, I should say that you have to do it to both sides if you do it to 1, to keep it equal. So now we would have 4 equals 4. If we didn't do it to this side, we would have 4 equals 3, and that's clearly false. And there are other properties of equality too. For instance, if I had 7 equals 7, to keep this equal, if I wanted to subtract 2, I would subtract 2 from this side. That would give me 5 equals 5. The way this shows up with variables is, let's say we have x equals 3. If we want to subtract something from both sides, let's say we want to subtract 3. What will happen is the equation we're given will have the same solution. Let's take a look and see. So x minus 3, well, we can't combine these two, right? These are two different things. In general, I recommend, if you're having trouble finding how to combine numbers and variables, replace all your variables with unique objects and replace your constant terms with a unique object. So let's pretend x is beach balls and -3 is -3 tacos. You can't subtract beach ball minus 3 tacos. It wouldn't make sense. So when it doesn't make sense, you keep it the way it is. And then like we talked about before, 3 minus 3 will give us 0. Now we have our linear equation in one variable. It's in that same form. It's just that a here would be 1. Of course, if you wanted to use the addition property of equality, you could add 3 again to both sides, and you'd find that we're still at x equals 3. Because you did it to both sides, the solution never changed. 3 minus 3 gives us 0, and up here we mentioned that x is going to be 3. Beyond that, there are also the multiplication properties and division properties of equality. Let's say, for instance, I have a fraction. Let's say I have x over 2 equals 1/2. Remember our idea of inverse operations. Fractions are really just division. This is x divided by 2, this is 1 divided by 2. If I want to get x all by itself, I have to get rid of the dividing by 2 step. The opposite of dividing by 2, multiplying by 2. What'll happen is 2x divided by 2, that'll leave you with just 1x, which we can call x. And 1/2 times 2 is just 1. It might also help to cross out your terms that undo each other. This gives us just 1x. Finally, with the division property of equality, let's say we had something like 17x equals 34. Whenever a number is right next to a variable, what it's really doing is multiplying. According to the division property, I can divide both sides by the same amount, and we'll have an equivalent equation. What can I divide by that'll get rid of multiplying by 17? If you said dividing by 17, you're correct. But remember, the most key thing is you can't just do it to one side. You have to do it to both. So 17 divided by 17, that's just going to give us a 1. So we have just 1x. 34 divided by 17 gives us 2. Last but not least, we had the 4-step approach to problem solving. This is something that we talked about in the class after our first class, but it is part of 1.1. This is just a way to kind of conceptualize word problems a little bit better, because oftentimes word problems are the most difficult to comprehend and to know what to do with. I can't tell you the amount of times I've stared at a word problem and just said, I have no idea how to start. This is how to start. This is a fantastic way to start. And it doesn't work for everybody. If you have a better method, please use your method. But this is just a recommended 4-step approach to solve problems. The first step is to understand the problem, figure out your unknown and what information is being given, and also what you're trying to find out in the end. The second step is to make a plan. The plan that we talked about in class is rough draft mathematics, which I'll demonstrate in a second. Number 3 is to solve the problem by carrying out your plan. Number 4 is the most important. Put your solution back into the problem and see if it still makes sense. If the question you're starting with is, Jenna has 2 marbles, Marcus has 3, how many marbles are there altogether? And you end up with 22 marbles, that solution doesn't make sense with regards to the original statement. That's why step 4 is so important. Let's take a look at some problems that demonstrate everything we've talked about. For this sheet, I'm only going to work on problems 1, problem 6, and problem 10. What I would recommend is that you do these on your own by pausing the video and checking to see how you do. Did you pause the video and try them out? If not, that's all right. I'm going to show you how we would tackle a problem like this. W plus 4 equals 16. Well, we got to think to ourselves. We want to get the W all by itself. That's how we know we've solved the problem, when W is alone. But there's a problem. There's a 4 attached to it, and it's attached by addition. Well, that's not a problem for us if we remember our inverse operations and our properties of equality. Because our W will still be the same even if we add, subtract, multiply, or divide something to both sides, as long as it's the same thing to both sides. In this case, we want to undo adding 4. So what's the inverse of addition? Well, subtraction. So we're going to subtract something from both sides. That something is whatever number is attached to our variable. So in this case, we want to subtract 4 here, because that will cancel out positive 4 with negative 4. But you have to do it to both sides. When you do so, positive 4 and negative 4, when you put them together, they make 0. And all I'm left with is W, just like I wanted. Now all I need to do is 16 minus 4, which is 12. Something that's a little bit trickier is when we get to multiplication division. A lot of students have a hard time remembering which step to undo. And it's mostly because you don't see an operation a lot of the time. You don't see a plus sign, minus sign, multiplication sign, division sign. But the key here is we want to get our q by itself. Attached to this q is the number 7. Whenever there is a number right before a variable, what it's really saying is that multiplication is happening between them. Think about it. If I replaced q with the word, I don't know, water bottles, this is saying 7 water bottles. This is saying 7 times 1 water bottle. So 7 times 1 water bottle is 7 water bottles. Anytime you see a number next to a variable, it's multiplication. So here, we take a look at 7 times q, and we think to ourselves, I want to get q by itself. So I have to do the inverse operation to multiplication. Well, that's going to be division, which I notate using the division bar, but you can use the division sign if you would like. What are we dividing by? Well, it's a 7 that's attached to the q, so to get rid of multiplying by 7, we have to divide by 7 on both sides. These two will end up canceling out, because 7 divided by 7 is 1, so I'm left with just 1q. 35 divided by 7 is actually going to give us our whole number answer of 5. Last but not least, I want us to take a look at one word problem, because you will see these. A coupon subtracts $17.95 from the price P of a pair of headphones. You pay $71.80 for the headphones after using the coupon. Write and solve an equation to find the original price of the headphones. What I would recommend is if you have not used the 4-step process to this point, keep your page open on page 5 and look at those 4 steps and see how I do each step as you follow along with the video. So, the first thing is we need to figure out what our unknown is. What don't we know in the problem? Well, we don't know the price P, the original price, to be specific. That's our unknown. Which means, by the end of our problem, after we write an equation and solve it, our price, P, should be all by itself. Beyond that, we also have a couple other pieces of information being given to us. We know that there's $17.95 somewhere in the problem. We know there's $71.80 somewhere in the problem. But there's also some other hidden pieces of information, which is what makes word problems a little bit trickier. We are also given the operation, what's being done, to the $17.95. the coupon subtracts $17.95 from the price P. So we know we're going to have subtraction somewhere. Additionally, we know that we end up paying, in the end, $71.80. Anytime you see the words like you pay, or you finish, or you end, or even just the word is, that tells us what the result of all of the math is. Anytime you have a result, that's usually going to mean it's on the other side of an equal sign. Now, I'm a math teacher, so I look at this problem and I know how to solve it. Not to brag. But for many students, if you look at this problem, you just have pieces of information that are disjunct. You don't know where to put them. They're sort of scrambled. This is where the process of rough draft mathematics comes in. Rough draft mathematics is just like a rough draft in English. It just involves getting something down on the paper so that when you look at it, you can edit it later. What this might mean for us is putting together pieces in orders that make sense to us and seeing if it works. So let me give you an example of some rough draft thinking. Okay? I know that I'm going to subtract $17.95 because it happens right in order. We subtract $17.95. So part of my rough draft is I'm going to write minus $17.95 right here. Right? Okay. I don't know where that's going to go, though. I know that I have my price P somewhere, so I'm just going to leave that floating around somewhere. And I know that I want, in the end, to have 71.80. And I know that one of these is going to be on the different side of the equal sign. For my first rough draft, let's say I'm looking at 71.80 minus 17.95 equals P. This is just a rough draft. I'm going to let you know this one is actually incorrect, but we'll talk about why. At first glance, this might make sense to us. 71.80 minus 17.95 will surely give us an answer. However, if we were to try this one out, we would find that our answer would be something like this. 71.80 minus 17.95. We get 53.85. We have to take it back to the context of the question. Would it make sense for the original price to be 53.85 if we got a coupon and ended up paying 71.80? No, a coupon's supposed to make the price go lower. Going from 53.85 to 71.80 is an increase. So, this was our rough draft equation, but it was not the correct one, and we keep trying. It turns out that because we're subtracting from the price P, that's another way of saying P minus 17.95 equals 71.80. Now, we don't know if this is correct or not yet, so we have to do some mathematics and figure out if P makes sense. To do so, we have to look at getting P by itself. Right now, there is minus 17.95 next to it. The inverse of subtracting is adding. And since we're trying to get rid of 17.95, that's what we're going to do to undo this one up here. Add 17.95 to both sides. These ones will cancel out to 0, giving us just P. And these ones, 71.80 plus 17.95, we end up with 89.75. Does this make sense in the context of the question? Let's see. To figure out if it makes sense, replace our variable in the question or our unknown in the question with the number. Now, we're not just going to replace it with just a number. This unknown is going to tell us what this number means. Because it's a price, I know that I could put a $sign behind it, or in some cases, maybe a cent symbol. So let's read it out. A coupon subtracts $17.95 from $89.75. You pay $71.80. Does that make sense? Yeah, it sounds to make sense to me. If you start with having to pay $89.75 and you use a coupon, that's $17.95. $71.80 sounds about where that coupon would get us. So that's how we know we've done our 4 steps correctly. Thank you so much, everybody. Have a fantastic rest of your day, and I will see you next time.